so we got an inequality, okay, where we have x squared minus 2x is greater than or equal to 8. Okay, so we're going back to a polynomial inequality. Okay, not a rational inequality, but a polynomial. Okay, so here we have x squared minus 2x is greater than or equal to 8. And if I convert this again to a comparison to 0 inequality, so I can just move the 8 over. So here I have x squared minus 2x minus 8 is greater than or equal to 0. And this format will be along the lines of what we have for f of x is greater than or equal to 0. Okay, so you have in this lineup, okay, so you have that f of x is equal to x squared minus 2x minus 8. And if I look at establishing the zeros, okay, of this particular polynomial, okay, so if I look at setting equal to 0, gotcha, okay. So we have for x squared minus 2x minus 8 is equal to 0. So if I look at factoring, so you have x squared goes to x and x. And so we have, in this particular layout, okay, so you have the sum of the outside and inside products would be negative 2x. So this will signal that more weight will be given to the subtraction than to the addition. Okay, so you have the quantity of x plus 2 times that of x minus 4, okay, is equal to 0. And if I set each of the factors to 0, so we have with x plus 2 is equal to 0, okay, I have x is equal to negative 2. And we have with x minus 4 equal to 0, okay, we'll have the x is equal to 4. Okay, so this is our function f of x. And now for the zeros upon which we will have the table of intervals to be established around, okay, so we have negative 2 and 4. And looking at what we have in the setup. Okay, so you have starting off, okay, so between negative 2 and 4. Negative 2 is the smaller 0. So the first interval section, okay, we have between negative infinity and negative 2. And then we have between negative 2 and positive 4. Okay. And then we have those values of x greater than 4. Okay, and looking at separating, again, the interval sections. Okay, so we have in the case of the first item, okay, so if I look at choosing inputs for sampling, okay, so you have for anything less than negative 2, we can go with negative 3. And then we have between negative 2 and 4, choose any value greater than negative 2 and less than 4. Okay, 0 will fit the bill. And then we have anything greater than 4, we can go with the number 5. Okay, and again, the function we are working with, we have f of x is equal to x squared minus 2x minus 8. Now for f of negative 3, okay, so if I plug in negative 3 for x, okay, now first item, we are looking at the square of negative 3. Then we have minus 2 times negative 3. And we have followed by the subtraction of 8. So the square of negative 3 is going to be a positive 9. Negative 2 times negative 3 is going to be a positive 6. And we have 9 plus 6 is 15 minus 8. So this will come out to a positive 7. Okay, now for f of 0, now the variable terms will become negligible and only minus 8 will follow. So right away we will have the f of 0 is equal to negative 8. And for f of 5, okay, so you have the square of 5 minus 2 times 5 minus 8. Okay, so you have 5 squared is 25. Negative 2 times 5 is negative 10. And we have minus 8. And we have 25 minus 10 is 15 minus 8. Okay, so like what we have with negative 3, okay, the output is also going to be 7. Okay. And so looking at the signed values throughout for f of x, okay, so we have first case, okay, we have a positive output. Okay, so f of x is going to be greater than 0. Then for the next, okay, we have a negative output. Okay, so we're going to have the f of x is less than 0. And we have for the last, okay, we have a positive output. So we're going to have the f of x is greater than 0. And so for what we have in the overall picture, now this is the inequality we started with. And again, just framing this where we have in the rewrite, okay, with a comparison to 0 inequality. And so we have in the form of f of x is greater than or equal to 0. And again, you have the same direction as where f of x is greater than 0. And since we are dealing with a polynomial as opposed to a rational function, again, you don't have any denominator in a fraction to worry about, and you do not have an even root in a radical to worry about. So the zeros we have here are going to be in the domain. So a polynomial is going to have all real numbers for the domain. So both negative 2 and 4 will create the equal to 0 parts. And so we have, in the case of the solution, okay, so in the same direction, it's greater than 0. So again, we are involving the limits. Okay, so you have negative infinity and negative 2. As well as 4 and infinity. And once again, infinities are boundless. Okay, so they will stay in the parentheses. And again, negative 2 and 4 will set the function equal to 0. So both of these values will be in the bracket. And in terms of graphing, okay, so this is your interval solution. But in the case, since it's said to graph, so for what you will have is that in graphing, okay, so you have okay, so you have a negative 2, which will be to the left of 0. We have positive 4, which will be to the right of 0. And for following through, okay, so for values less than or equal to -2, so -2 is included, and this will be indicated by a solid point. And from this, okay, we're going to have an array that is going to go continuously to the left. Okay. And that is technically going to be approaching negative infinity. And we have at the upper end, okay, for values of x greater than or equal to 4. Again, so we're going to have 4 included. Okay, so you're going to have not an open circle, but a closed point. And here we're going to have array running continuously, and that would be heading out continuously to the right. And then we have going out to infinity. All right, so that'll be your graphing solution for what we have in number 15. All right, and in the case of what we have with number 16, okay, so we have a polynomial that is given in factored form, where we have x plus 2 times x minus 4 times x plus 6 is greater than 0. Okay, and for this one, we already have a comparison to 0 layout. Okay, we can say that the form is going to be where we have f of x is greater than 0. Okay. And if I were to set this function equal to 0, and that is so as to be able to identify the zeros. And we can do this rather quickly. Again, so all the factors are given in direct fashion. And again, a polynomial that we have where the presentation is again in direct fashion, the domain will be the set of all real numbers. Okay, so for x plus 2, we have x equal to -2. For x minus 4 equal to 0, we have x is equal to 4. And as for setting equal to 0, the binomial x plus 6, okay, we have x equal to -6. Okay, so we have, again, just for what we're going to be using to test out, okay, we have f of x equal to, once again, the product of x plus 2, x minus 4, and x plus 6. And for the zeros, okay, so you have -2, +4, and -6. And setting up what we have for the intervals. Okay, so looking at starting from negative infinity, we're going from negative infinity approaching the smallest of the zeros, okay, which would be -6. And bypassing -6, so we're going past this and approaching the next smaller zero, which in this case will be -2. Okay, and then we have going past -2, and we have approaching but not including 4. And let's see, and we have going past 4 all the way out to infinity. Okay, and for what we have in the case of the tested values, that can be supplied. So anything less than -6, we can go with -7. Between -6 and -2, let's go with -3, and we have between -2 and 4. We can go with 0, and anything greater than 4, we can go with the number 5. Again, we're looking at testing out our function. F of x is equal to x plus 2 times quantity of x minus 4 times that of x plus 6. Okay, and just partitioning the interval sections. And again, so -7 is a value that is less than -6, and -3 falls between -6 and -2. And again, we have 0 between -2 and 4. And again, 5 is just one among many examples that we can use for inputs, any input that is greater than 4. Okay, so we have looking at the function values. Okay, so we have for the first one, okay, for f of -7, okay, so you have -7 plus 2 is -5, and we have -7 minus 4, so that is -11, and -7 plus 6 is going to be -1. So you got -5 times -11 is a positive 55. However, when multiplied by -1, okay, we have a -55. And for f of -3, now we have -3 plus 2 is -1. -3 minus 4 is -7. -3 plus 6 is a positive 3. And taking the product, so this is going to be a positive 21. For f of 0, okay, so you have 0 plus 2 is 2. 0 minus 4 is -4. And we have 0 plus 6 is 6. And the product of these three numbers will be -48. And for what we have in the case of f of 5, 5 plus 2 is 7. 5 minus 4 is 1. 5 plus 6 is 11. So we have for this product, okay, this will come out to a positive 77. Okay, in the case of the sign of f of x, okay, so for the first, okay, we have a negative output. So we're going to have the f of x is less than 0. Then we have for the next, we have a positive. So we have the f of x is greater than 0. Then we have next a negative. So we have again f of x is less than 0. And for the last, okay, we have a positive. And so we have f of x is greater than 0. And so for going back to the original inequality, okay, so referencing again where f of x is greater than 0, it's going to turn out that for the solution, Okay, so we're going to have exclusively the use of parentheses due to the lack of an equal sign. So where f of x is greater than 0, we have values of x such that negative 6 is less than x is less than negative 2. And again, we have along with those values of x such that x is greater than 4. So that will be the interval solution for what we have in the case of problem number 16. All right. Now we looked at number 17 and 18 the other day, and for what we have in the case of number 19, okay, so here we have a comparison inequality, okay, where you have comparisons between non-negligible quantities. And here we have x plus 8 over x minus 1 is greater than or equal to negative 2. And looking at what is going to be in the solution set. Okay, so if I rewrite this, okay, as a comparison to 0 inequality, so I can move this number over and rewrite in terms of adding. And what I want to do here is combine these terms together. So just make into a consolidated expression. Okay. So in the case of x plus 8, over x minus 1 plus 2, what I want to do here is write 2 in terms of a fraction, okay, where the denominator is at x minus 1. So what I can do here, I already have x minus 1 in the denominator for the first ratio. But now for 2, I can write this as 2 over 1. And just raise this in terms of a fraction over x minus 1. So I can multiply by 1 in the form of x minus 1 over itself. Okay, so for 2, as a fraction over x minus 1, if I distribute 2 over the quantity of x minus 1, so this will be 2x minus 2. And if I cluster together the numerators, so I have x plus 8, okay, and the addition is what separates the ratios, so there will be no sign change. So for now, 2x minus 2 will stay as it is. And combining the numerator terms, so we have x plus 2x becomes 3x. 8 minus 2 becomes 6. Okay, so for what we have all together, okay, this will come out to 3x plus 6 over x minus 1. Okay, so just putting all together. Okay, so you have this form. You see we have f of x or r of x is greater than or equal to 0. And so just as a bit of an aid in terms of setting up our table. Okay, so we have r of x to turn out to be 3x plus 6 all over x minus 1. Now for the zeros, from the numerator, if I set 3x plus 6 equal to 0, and we have 3x equal to negative 6. And from this, I'm going to have x equal to negative 2. And since negative 2 stems from 3x plus 6, which is in the numerator, and there's nothing about it that is in the denominator, we can say that negative 2 sets the function equal to 0. So that 0 is in the domain. But now for x minus 1, that is in the denominator. And if I set this equal to 0, we have x equal to 1. But if I have x equal to 1, you're going to have the bottom part of the fraction set equal to 0, and that would render the rational expression as undefined, since you cannot divide by 0. So 1 is not in the domain. And for what we have in the case of setting up the intervals, okay, so we got with the zeros, the lesser of the two is negative 2. So you have those values of x less than negative 2. And then you have those values of x greater than negative 2 and less than 1. And then we'll have those values x which will be greater than 1. Again, so just looking at setting up our test values for the input. Okay, so anything less than negative 2, we can go with negative 3. Between negative 2 and 1, we'll just go with 0. Anything greater than 1, we'll go with 2. Again, we have with our rational function to test out. Again, we have r of x equal to 3x plus 6 all over x minus 1. Okay, and after I separate the interval sections and looking at what the outputs will be among the interval sections, so we have with, first of all, we have r of x equal to 3x plus 6 over x minus 1. So we have an r of negative 3. Okay, so I have initially, okay, so you have 3 times negative 3 is negative 9 plus 6 is going to be negative 3. Negative 3 minus 1 is negative 4. Negatives will cancel. So we have this rational expression on the positive side at 3/4. For r of 0, okay, we have 0 plus 6 is 6. 0 minus 1 is negative 1. So r of 0 comes out to negative 6. And for r of 2, okay, you have 3 times 2 is 6 plus 6 is 12. 2 minus 1 is 1. And so that will end up as a positive 12. Okay, for the sign of r of x, okay, so you have a positive for values of x less than negative 2, so we have the r of x is greater than 0. Then we have next that output is negative, whereby r of x is less than 0, and then we have for the last, okay, we have a positive, whereupon r of x is greater than 0. And it's going back to our inequality. Okay, so again we had x plus 8 over x minus 1 is greater than or equal to negative 2. Once I consolidated and formed this comparison to 0 inequality, again, so we have r of x, or 3x plus 6 over x minus 1 is greater than or equal to 0. And this will be in the same direction as where r of x is greater than 0. Now, for what we have in the case of the solution, again, that equal to 0, okay, presents the possibility of there being at least a bracket in this interval solution. So we have involving the limits. Okay, so you have negative infinity, and negative 2. Let's say have 1 and infinity. And for the enclosures, okay, so infinities are boundless. So you have parentheses around the infinities. Now for negative 2 and 1, okay, now you'll have a bracket as long as the 0 is in the domain and officially sets the rational function equal to 0. So negative 2 is in the domain, so that creates the equal to 0 part, whereas 1, it creates an undefined situation. So 2 is in the domain, so this will go in the bracket, whereas 1 is going to be in the parentheses. Okay, so that is going to be the interval solution for the inequality posed in number 19. All right. Now, looking at what we have among the other components from your test review set, and I'll tell you what, just I'm going to kind of, in terms of the quadratic functions, okay, we'll kind of go back to those tomorrow. But just some items we can just kind of go through pretty quickly. We have for question number 3, okay, so, and it says here to solve for w, whereupon we have w squared plus 10w plus 24 times the quantity of 5w minus 15 is equal to 0. And we have for this one, now you could expand out and factor. Or you can go ahead and apply the zero product property and then factor afterwards. Okay, so for this product to be equal to 0, these factors have to be 0. So just for the w squared plus 10w plus 24 part, if that is equal to 0, and we can factor this trinomial to w plus 6 and w plus 4. And itemizing case, so we have for w plus 6 and w plus 4 equal to 0. So we have for w plus 6, we have w equal to negative 6. And for w plus 4, okay, we have w is equal to negative 4. Now for 5w minus 15, if that is equal to 0, now you can either factor out 5 or divide the whole expression by 5. And we'll just factor in this one. So if I factor 5, we'll have 5 times the quantity of w minus 3 is equal to 0. And now 5 is just a multiple. It's just like a constant. It's not doing anything immediately to w by itself. It's not adding, subtracting, multiplying, or dividing w. It's just a multiple. Whereas with our w factor in the mix, okay, we have w minus 3. And if that is equal to 0, then we have that w is equal to 3. So we have, in the case of our solutions for w, okay, we have -6 and -4 from the first factor, and then from the second and last, okay, we have that w is equal to 3. So there will be a trio of solutions for w. Okay. Again, that is result for problem number 3. And looking at what we have, let's see, for the next item. Okay, all right, so we're looking at zeros and multiplicities. Okay, and here we have polynomial, okay, that is given in factored form. And in the case of 4, okay, so you have f of x, you have equal to 6x times the quantity of x plus 9. And we have times, okay, the square of x minus 5. And we have times the quantity of x plus 11 raised to the third. Okay, so we're looking at zeros and multiplicities. Okay, so multiplicities, okay, you're stating or stressing the degree of each of the variable factors. Okay. So we have in this particular case, right? So we have, now 6 is just a multiple. Now we have with our factors. Okay, so you can say we have 6x is equal to 0. If I divide by 6, so we'll have that x is equal to 0. For x plus 9 equal to 0, okay, we have x is equal to -9. For x minus 5 is equal to 0, okay, we have x is equal to 5. And for x plus 11 equal to 0, so you're going to have that x is equal to -11. Okay, so just for the zeros, okay, and so for this item, okay, so we got, okay, it says list each zero of f according to its multiplicity. Okay, and so in the case of the zeros, okay, so you have with our zeros, okay, so we got 0, -9. Now we have 5. And also we have -11. Okay, and for 0, okay, this stems from the x factor, where we have 6 times x. And if you notice, there was no explicit degree for x. So if you don't see any raised power or explicit power for x, you would read this as if it happened to be x to the first. So 0 is multiplicity 1. Likewise with -9, this stems from just x plus 9, and read that as x plus 9 to the first. So -9 has a multiplicity of 1. Now for 5, this comes from x minus 5, which is raised to the second. So x equals 5 is going to be a 0, which has a multiplicity value of 2. And for -11, x equals -11, this comes from x plus 11, raised to the third. And the 3 is going to stress not only the power to which x plus 11 is raised, but also the multiplicity that defines the 0 value of -11. So minus 11 is going to have a multiplicity of 3. Okay, now for what we have in the case of the fifth item, it says to list all x-intercepts and y-intercepts of the graph of the function, where we have f of x is equal to 2x cubed plus 2x squared minus 24x. Okay, and I think I can squeeze this in. So again, we have for the x-intercept or intercepts. Okay, so you're looking at setting y or f of x equal to 0. And for what we have in the mix, okay, so if I look at factoring, now the greatest common factor of 2x cubed, 2x squared, and negative 24x, okay, that's going to be 2x. And so we're going to have x squared plus x minus 12. And I can factor further, where for x squared plus x minus 12, this can go to x plus 4 and x minus 3. Okay, so looking at what we have among the factors, so if I have 2x is equal to 0, I have x is equal to 0. If x plus 4 is 0, okay, so you're going to have the x is equal to negative 4. If x minus 3 is equal to 0, we're going to have the x is equal to 3. Okay, so it's going to follow, okay, now for the x-intercepts. And there are two versions of this. Okay, one is just stating putting in equality terms. Okay, so we have x equal to 0, x equal to negative 4, and x is equal to 3, but in coordinate fashion. When x is equal to 0, okay, we have the origin, so you have the ordered pair 0, 0. X equals negative 4, and that's going to be on the x-axis at negative 4, 0. And for x is equal to 3, okay, this will occur on the x-axis at 3, 0. And in the case of the y-intercept, okay, so we're looking at solving for y as x is set to 0. So in this case, you have y is equal to f of 0. Again, f of x is a functional notation for y, and with x at 0, and guess what? So you have 2 times 0 cubed plus 2 times the square of 0 minus 24 times 0, and all of these will come out to 0. So then we have that y is equal to 0. And so we're going to have for the y-intercept, okay, in equality statement terms, you have y is equal to 0, but in coordinate fashion, like where you have 0y, that's going to be also an x-intercept. Okay, so we are referencing once again the origin, okay, which is the ordered pair 0, 0. Okay, all right, so those would be the intercepts, okay, for that particular function. All right, now for what we have in the case of the next item, let's see, it's number 6. We'll look at number 6 later. For number 7, yeah, this is a good one to continue with. Okay, so you have, it says here, below is the graph of a polynomial function, f, with real coefficients. And it says to use the graph to answer the following questions about the function. And, okay, so we have, for this one, okay, you have, you have, like, your relative minimum and maximum points. And we have, just in the layout, it says we're to look where the function is going to be increasing, and to choose all the intervals that are going to apply. Okay, so for what we have here, let me try to do, if I can get this graph to appear. Yeah, just have a pretty good view on this one. Okay, so you have, so you're looking at increasing over which intervals. Okay, so where we have increases, let's kind of use okay, so where we're going to have increases, okay, so you have a decrease, but you're going to have an increase. In this particular zone, have another increase. And then we have yet another increase. Okay. Now for the intervals, okay, so for this first item, okay, so let's say we're going between -7 and -5. That's going to be over here. And then for the next increase, okay, looks like we have between -2 and +3. And there's one more section of increase, and that's going to be between 6 and 8. And if you notice for the other ones, like between -infinity and -7, that's a decrease. Between -2 and 6, if you notice between -2 and 6, okay, you have between -2 and 6, so it looks like you have an increase and a decrease. So there's a bit of static here. So, but you want to look at where the activity is going to be increase only. In the case of past 8 on out to infinity, that is a decrease only. Okay, now, and it says the function f has local minima at which x values. Local minima at which x values. Okay, and so we have for local minimum. Okay. Okay. Okay, so just kind of doing some color coding here. So this is going to be like, again, sort of your dipping points. Okay, so in terms of which x values, so you have -7, and you also have at -2, and also we'll have at +6. Okay, so the function f has local minima at which x values, so you have at -6, -2, and also, once again, we have at +6. And now, it's asking what is the sign of the leading coefficient of f. Okay, and what's going to happen here is that, okay, you got your end behavior, which would be up to the left, down to the right. So just kind of providing some cues here. Okay, and what is going to happen here is, say if the end behavior is up to the left and down to the right, that means that your leading coefficient is going to be a negative value, and the degree is going to be odd. Okay, so the leading coefficient, okay, that is going to be negative. Okay, and it's asking now, okay, which of the following is a possibility for the degree of the function? So leading coefficient is negative. Now, again, if you have up at one end, down at the other, you're going to have the degree to be an odd value. But if it had to be both up or both down at the extreme ends, the degree would be even. Now, and just reapplying what we have for the function itself, and I'm just going to put in once again, see if I can do it. Yeah. So what's going to happen here is that we can count up the number of turning points. Okay, so that's just combining the number of minimum, local minimum, and local maximum points. And again, n is odd. And again, the number of turning points will be less than the degree. So again, the number of turning points is going to be less than the value of n. Okay, n is odd. So you're looking at where, in effect, you have turning points. So you're going to have like 6 is going to be less than, and if n is odd, you got like 7, 9, 11, and any other odd value that would follow. Okay, so for what here we have here, just for what it could possibly be from this list. Now it cannot be 5, since 5 is, even though it's an odd number, it is less than the number of turning points. So for your possible values here, okay, so your odd number that is greater than the number of turning points, that's going to be 7 and 9. And so we're limited to just those two amounts from the list. But it could be 11 or 13, but we don't have those higher odd numbers in the list. Okay, now for what we have with regard to question number 8, it says to find a polynomial f of x of degree 3 that has the following zeros. Okay, so you have -3, 1, and 0. And it says to leave your answer in factored form. And I'm just going to mention both of these. Okay, for the factored form, okay, so we would have f of x is equal to, and for, say if I have x equal to -3, we can say that stems from x plus 3. For 1, okay, we have x minus 1. And for 0, can we say we have at x. Okay, now I'm just going to mention this. Okay, if I were looking for the expanded form, okay, so if I have like x plus 3 times x minus 1, and I multiplied those first two functions together, so I have like x squared got minus x plus 3x, so that's going to be plus 2x minus 3. Okay, I have multiplied by x. So if I were to expand, I would have x cubed plus 2x squared minus 3x. But just for the factored form, this is going to be the results. Okay, but for the expanded form, one of these will be f of x equal to x cubed plus 2x squared minus 3x. All right, and we have just a reminder, and just going back to what we have with polynomial division. And for the case in number 9, okay, so we have in this one, so we have a polynomial function 9x cubed plus 18x squared plus 17x plus 6 is divided by 3x plus 1, and it says to give the quotient and remainder. Okay, so you had the divisor. Okay, so you have 3x plus 1 again we have taking into, so you got 9x cubed plus 18x squared. Then we have plus 17x plus 6. Okay, now there might be a temptation to try to set this up along the lines of synthetic division. Okay, but if you notice, okay, with synthetic division, you can go directly into that if you had the divisor to be a linear expression, which this is, but you want the coefficient to be only 1, and here we have 3 in front of the x. If I had like just x plus 1, I'd be like, by all means go for the synthetic division, but with the 3 in front of the x, this is where you have to hit the brakes on the synthetic division. And for what we have for this problem, okay, so if I go with long division, again we have with long division, we're looking at row by row subtracting, and we have no missing degree terms from the dividend. So we have a 3x into 9x cubed, or 9x cubed divided by 3x, so this is going to be 3x squared. Then we have with distributing, so we have 9x cubed, and we have plus 3x squared. And looking at subtracting, so 9x cubed goes out. 18x squared minus 3x squared, so this will be 15x squared. And 17x and 6 have been untouched. I'm just going to bring those down. Now we have 3x into 15x squared. So this will go 5x times. And then we have in distributing, so you have 5x over 3x is 15x squared. 5x over 1 becomes 5x. And subtracting again, okay, we have 15x squared will go out. Then we have 17x minus 5x, which will be 12x. And I can bring down the 6. Now I took 3x into 9x cubed, which was 3x squared. Then I took 3x into 15x squared, which was 5x. Now I'm taking 3x into 12x, which is going to be at 4, and distributing. Okay, so 4 over 3x is 12x, and 4 times 1 is 4. And we have upon subtracting, 12x will go out, and we have 6 minus 4 is 2, and I cannot take 3x directly into 2, so 2 is the remainder, while 3x squared plus 5x plus 4 is the quotient. Okay. Again, so we have with the quotient, we have 3x squared plus 5x plus 4. And for the remainder, again, that is going to be at 2. All right. Now, where the synthetic division comes in, and we have for number 10, and we have for this particular layout, it says here to use synthetic division to find the quotient and remainder whenever we have 2x to the 4th plus 10x cubed plus 9x squared minus 7x plus 5 is divided by x plus 3. Okay, and I'm just going to kind of give you just a setup here. Okay, so again, from the long division perspective, Again, you have x plus 3 into 2x to the fourth plus 10x cubed plus 9x squared minus 7x plus 5. And again, if you use synthetic division, you don't take x plus 3 or plus 3. Remember, okay, now the leading term in the divisor is x, not 3x like what we had in number 9. So we have only x at the front, and x is a first order. So I can just take the 0 of x plus 3. So I have x equal to -3. And again, just for the layout, okay, so you got -3. Again, the display is a little different, but I got -3 partition, and then you have the coefficients of the dividend. So again, I have 2, 10, 9, -7, and 5. And just for the setup, okay, so we have with the leading coefficient from the dividend, just bring that down. -3 times 2 is -6. And again, we're formulating column by column addition. So 2 is brought down, -3 times 2 is -6. 10 plus -6 is 4. -3 times 4 is -12. 9 plus -12 is -3. -3 times -3 is 9. -7 plus 9 is 2. -3 times 2 is -6. And 5 plus -6 is -1. Okay, so again, just I might have enough room here. Let's see. Now just squeeze those in. Okay, so we have with the numbers. Okay, so 2 is brought down. -3 times 2 is -6. 10 plus -6 is 4. -3 times 4 is -12. 9 plus -12 is -3. -3 times -3 is 9. -7 plus 9 is 2. -3 times 2 is -6. 5 plus -6 is -1. And then you have with the tight fit over here for this first box and the second. Okay, now the second box is just going to be the remainder. Okay, so the remainder is going to be at -1. And for what we have right in front of this, the 2, 4, -3 and 2. That's going to be the quotient. So again, after 2 is brought down, it now references 2x cubed plus 4x squared minus 3x plus 2. Yeah, you can't fit all that into that little box. Okay, so this result here, we have -1. In this part, you have 2x cubed plus 4x squared minus 3x plus 2. All right, and in the case of what we have regarding the remainder theorem, okay, and this is just looking at, it says to give the quotient and remainder for the associated division and value of P of 2. Okay, so we have for number 11, okay, so you have P of 2. So you got P of x equal to x to the fourth minus 2x cubed minus 5x squared plus 3. Okay. And it says give the quotient and the remainder for the associated division and the value of P of 2. Okay, so you're looking at P of 2. Right. And now, for what we have here now, P of 2, okay, we're using this particular 0. And if I take what I have along the lines of say for the long division setup. Okay, so you have with 2, we say that 2 is the 0 of x minus 2. And we have with the dividend, so you have x to the 4th minus 2x cubed minus 5x squared. Notice we do not have a first order x term, so I need a 0 placeholder for this. We have plus 3. Now, in the case of taking what we have along the lines of synthetic division, so if you notice you have x minus 2, and the 0 of x minus 2 again is going to be at 2. So with synthetic division, okay, so I got 2, and lining up, so you have 1 for x to the 4th, negative 2 in x cubed, negative 5 for x squared. Again, you have 0 for the omitted x term of first order. And again, you want the dividend to close out with a constant. So we have with the synthetic division, so 1 will be brought down. 2 times 1 is 2. Negative 2 plus 2 is 0. 2 times 0 is 0. Negative 5 plus 0 is negative 5. And 2 times negative 5 is negative 10. 0 plus negative 10 is negative 10. And 2 times negative 10, okay, that will be negative 20. And 3 plus negative 20 is minus 17. Okay, so in this particular case, the remainder is going to be at negative 17. Now for the quotient, now I'm going from 1x to the 4th to 1x cubed. And guess what? I got 0, so that means we have 0x squared, or you can bypass the x squared part since that is going to be negligible. So we have x cubed minus 5x minus 10. So that is going to be the quotient. And again, the remainder is going to be minus 17. Okay, and it says, and now for p of 2, if looking for the value of p of 2, I'm just going to restate this. Okay, so for p of 2, so I have like 2 to the 4th minus 2 times 2 to the 3rd minus 5 times the square of 2 plus 3. 2 to the 4th is 16. And 2 cubed is going to be 8. And that will be multiplied by negative 2. And we've got negative 5. Now 2 squared is 4. We've got 16 minus 20. Plus 3, and guess what? 16 minus 16 is 0. Then we've got negative 20 is minus 20 plus 3, and so that will come out to negative 17. And guess what? The remainder and the function value, those will always be the same. Okay. Now, for what we have in the case of the factor theorem, Okay, and it says to use this one to determine whether x plus 3 is a factor of p of x is equal to x cubed plus 4x squared minus 9. Okay, and what you can do here, you can actually go about it either of two ways. Okay, so you have with x plus 3. So we have with the long division setup. Okay, so you have x plus 3. Taking into x cubed plus 4x squared. Now we are missing a first order x term. And we have the negative 9 that follows. So that is your long division setup. Now, for synthetic division, if x plus 3 is equal to 0, so we have that x is equal to negative 3. And translating what we have in terms of synthetic division. So got negative 3, and lining up the coefficients. So you have 1 for x cubed, 4 for x squared. Again, 0 for the missing first order x term. We have minus 9. So we have with the synthetic division. So again, 1 is going to be brought down. And you have negative 3 times 1 is negative 3. 4 plus negative 3 is going to be 1. Negative 3 times 1 is negative 3. 0 plus negative 3 is negative 3. Negative 3 times negative 3 is a positive 9. Negative 9 plus 9 is 0. And guess what? The remainder is equal to 0. Now, if we were looking for the quotient, the 1, 1, and negative 3 would signify that we have x squared plus x minus 3. Okay, now, for what we have in terms of filling in the blanks, okay, so you have p of blank is equal to blank. Okay, so for the first, what we have in parentheses is going to be the 0. So I'm kind of use a bit of color code here. I'll go with the orange. Okay, so you have p of negative 3 is equal to what the remainder is going to be. So yeah, p of negative 3 is equal to 0. And if the remainder is equal to 0, then it is a factor. Had the remainder been a non-zero value, then x plus 3 would not have been a factor. So p of the 0, okay, is going to turn out to be not only the function value, but also it's going to be the remainder if you were to apply long or synthetic division. So x plus 3 is going to end up as a factor.